We have a couple of not all that related topics for today's video: alternating current and drift velocity. You've probably heard of alternating current, often called AC, as opposed to direct current, which is DC. If we were to plot the current over time with a direct current circuit, you just have a constant current going in one direction. With alternating current, as the name implies, it alternates one direction and then the other. So let's check out the difference between direct current and alternating current in a couple of simple circuits. Here I've got a battery. Batteries are typically always direct current sources, so the electrons are just going around in one direction through our light bulb. Over here we've got an AC source. I guess this wire is kind of in the way, but for an AC source, this could be an AC generator at a power plant or something like that. And that is going to create an alternating voltage, which is going to create an alternating current. And so these electrons are sloshing back and forth, one direction and the other. Now in most typical AC circuits, like in your house, they slosh back and forth at 60 hertz. And so that's a full cycle, so the power is actually off 120 times every second. And that's so quick that you don't typically notice. You have devices that are designed to run off AC, motors and whatnot, and your light bulbs, the old incandescent kind, in that 1/120th of a second, they didn't have time to cool off, so they actually were glowing the whole time. The new types of light bulbs, the compact fluorescents, they actually are flashing 120 times every second, and you could measure that. LEDs, I'm not sure how those work with the on and off cycle. I'm guessing they're on the whole time, but maybe not. I guess we should try to measure it. Alright, back to the presentation. So if we're going to get equations for our voltage and current as they're alternating, we just need to throw in a sine function multiplied by some V naught. This typically represents the maximum displacement, right? Because that's like the amplitude of the wave, so that's your maximum voltage. And then if you plug in this guy for your current equation into V equals I times R, then you also get a sinusoidal oscillation for your current being multiplied by some maximum value. If we want to look at the power in an alternating circuit, since power, you're either going to have I times V or I squared R or V squared over R. Either way, you're going to end up with a factor of sine squared, which is nice because then you never go negative. You just always have positive power. It's just going up and down. And it turns out that your average power, which is what we're often interested in, average power here, is going to be the average of I squared R, which will work out to be right in the middle between the top and bottom of this function here. So you're going to get 1/2 times your maximum current squared times R, or in terms of V, it would be 1/2 times the maximum voltage squared over R. So this will be useful for calculations here. Often that's what we're concerned with, is the average power. Now if we want to know the average current or the average voltage, well, the current varies like this. It's not sine squared, it's just a sine wave, right? The average value of this, I average, I guess we do I bar, right, is equal to a big fat 0. So that's not very useful. So we define this other value, the root mean square current, which is the similar idea, the same idea that we've seen with the root mean square error, where in order to cancel out the positive and negative stuff, you square the values, then you average them, and then you take the square root so that you're back down to amps instead of amps squared in this case. Now if we think about taking our current and squaring it, we're going to get a graph just like that power graph, where it's going to go up and do something like this, but it's always going to be positive. That wasn't drawn very well there. And the average right here is just going to be the peak current, the maximum current. We've squared it here. It's going to be that max current squared over 2. So if we then take the square root of that, we've got I naught squared over 2, and square root that, we are going to get I naught over square root of 2. And this is our RMS current, you can do similar analysis for RMS voltage. 1 over root 2, you're always around 70% of your maximum current is your RMS current, and the same thing for the voltage. And the nice thing about these RMS values is that our power equation that we've grown to know and love still works perfectly as long as we use our RMS values. And in fact, I said in the previous video that in household circuits the voltage is typically 120. That is the RMS voltage. The peak voltage is actually higher than that by a factor of root 2. So let's look at an example. We have a 1000-watt hairdryer connected to a 120-volt line. This, once again, is the RMS voltage. And we're trying to find two things, the resistance and the peak current. So to find resistance, we need I and R. So we're going to find the peak current first. So we can use power equals IV. As long as we're finding the RMS values here, then we're good. So to start out with, we'll find the RMS current, which is P over V, which is 1000 over 120, which gives you 8.3 repeating. So from this point now we can find either of these things. To find the resistance, you've got V equals I times R, so R equals V over I, which is going to be 120 divided by 8.3, and that is going to give us a little over 14 ohms is the internal resistance of our hair blow dryer. Okay, if we want to find the peak current from the RMS current, which is what this is, then we need the relationship that I RMS equals the peak current divided by root 2. So to find peak, we're going to take I RMS times root 2, which will give us 11.79 amps. So a bit more than the average or root mean square current. Alright, on to our next topic. In order for current to flow in a wire, those charges in the wire need to feel a force. And if they're feeling a force, that means that there's an electric field present. Now the first thing you should be thinking is, wait a minute, Mr. Giusti, you told me in conductors there is no electric fields. Well, that is true in electrostatics, but we are no longer in electrostatics. If we have currents flowing, then there definitely are electric fields inside there. As soon as the current stops flowing, the electric field has to go to 0. But while it's flowing, we're okay. Now we're going to define this other property. We use a symbol J, and it is the current density, which is defined as the current divided by the cross-sectional area. So if you have a wire, it would be the area of the end of the wire right here. Essentially, it's the area perpendicular to the direction of the current flow. And we can do some other substitutions. I'll spare you the derivation, but we can also define this current density in terms of the electric field and the resistivity. So a couple of things we have already seen. Alright, now another thing that we're interested in with electrons moving around is what we call the drift velocity, which we signify with V sub d. So back to my other picture, the electrons moving through this wire here are actually bouncing around all over the place with random motion, but they have some net movement in the direction of the current. Well, I guess the electrons would be the opposite direction of the conventional current. So they're moving really quickly as far as their velocity in any direction, but the progress they make is actually not all that big, which I will show you here in a minute. So to get at this idea of drift velocity, first thing we're going to do is we're going to say, well, the amount that the electron moves down a wire, we're going to call that delta x, and it's going to be the drift velocity times the time. We're also going to say that the volume of that wire, let me rewrite that. I'm going to write VOL every time I write volume so we don't get it mixed up with drift velocity or voltage or all the other V's we have to deal with. Okay, so the volume is the cross-sectional area times the length, or the delta x, of the wire. And so we can substitute in Vd times T for that delta x. So here's one relationship that we're going to use. Now jumping to something else, the amount of charge moving through a wire, delta Q, is the number of charge carriers, N, times the charge per charge carrier. Okay, and we're going to define something else that we're going to call the particle density. So it is the number of particles per unit volume. And if I rearrange this, I can say that this is N times the volume here, times Q. And since we're dealing with electrons, we're going to just go ahead and put in E here for the charge on the electron. And now, you can probably guess it, we're going to plug in this guy for our volume over here. So we're going to get N times A times drift velocity times time. Okay, now if we define our current as change in charge over time, well, this is change in charge, so if we divide that by time, that t goes away, and we get NA times the drift velocity. I think I forgot an E in here. Yep, there's an E. Got it now. Okay, and the last thing we're going to do is this current density here, which was I per area. Well, this is I, and then we just divide by area, so that area goes away. And we've got a nice little expression here that relates the drift velocity to the current density. So we're going to use that in an example. I want to make sure to write that one down. You're going to use that one later. I guess, yeah, that's probably all you need. Alright, so here if we have the diameter of a copper wire, and we know the current, and we want to find the current density. Well, the current density is pretty straightforward. It's just I over area. So all we have to do is take this 5 amp current and divide by the area of a wire with a 3.2 millimeter diameter. So the area is going to be pi r squared. So that's 0.0032 over 2, because we're converting diameter to radius, and make sure and square that. So our current density works out to be 6.22 times 10 to the 5th amps per square meter. Now that might look like a pretty large number, but a square meter is quite a large wire as well. So we're saying that if we scale up this small wire to something quite huge, then we would have a whole lot of amps running through it. Okay, now we want to look at the drift velocity of free electrons. So we can use that equation that we had earlier, where we've got J equals NE times the drift velocity. Now the tricky part in this equation is figuring out N here. That's the number of charge carriers, or the number of electrons per unit volume. So it's N over volume. And if we assume that the number of electrons, of free electrons in copper, is proportional or about on par with the number of atoms per unit volume, then we can say, well, I can take the number of atoms in a mole, Avogadro's number, divide that by the volume, which I can find by doing the molar mass divided by the density, the actual mass density here, because density is mass over volume, so volume is mass over density. Anyway, I'll spare you plugging in the numbers, but if you look all those up, you'll get 8.4 times 10 to the 28th atoms, or in our case, we're going to assume these are electrons per cubic meter. And at this point, we can plug into this equation up here. So we've got our drift current, 6.22 times 10 to the 5th. Then we've just found N here, times 10 to the 28th. Charge on a single electron, 1.6 times 10 to the negative 19th. And then we solve this for the drift velocity, which works out to be 4.6 times 10 to the negative fifth meters per second, which is actually incredibly small. If you invert this, so you have seconds per meter, and then convert it to hours, it works out to be about 6 hours for the electrons to travel 1 meter down a wire. So even though they're bouncing around at crazy speeds, the actual progress they make down the wire is small. Now, this doesn't mean there's a long delay between when you connect a battery or turn on a switch and when the electrons get to the device, because the electrons are already there. The analogy is like you have a pipe already full of water, and so when you start adding water to one end, the water comes out immediately of the other end. So same ideas with electrons. You add some electric field, give some electrons energy on one end, that's going to be communicated through your wire nearly instantaneously. Not quite, but close. Alright, that's all. See you next time.